Hello, welcome to my video series of data structures. This is part 3 of Module 6, the heap data structure. In this video, we will discuss the heap construction procedure. In the previous videos, we discussed the find best, insert, and delete best operations for heap. We learned that the find best operation can be executed in constant time, while both insert and delete best operations have a time complexity of O log n. In this video, we will focus on the construction function and explore how to build a heap efficiently. The construction function is responsible for building a heap from a set of n unsorted data elements. There are two naive approaches to construct a heap. In the first approach, we start with an empty heap and insert the data elements one at a time. As the heap grows, it may contain up to O(n) data elements. In this case, each insertion into the heap requires O log n time. Since there are n elements to insert, the overall time complexity becomes O(n) log n. In the second approach, we first sort the data elements and then load the sorted elements into the heap's internal array. The sorting step dominates the process, leading to an O(n) log n time complexity. Note that the data elements in a heap are only partially sorted. While fully sorting the data elements requires O(n) log n time, partially sorting them, which would be sufficient for constructing a heap, could be achieved more efficiently. Next, we will introduce a heap construction procedure that leverages this principle to build a heap in linear time O(n). Given a set of n unsorted data elements, the first step is to load them into the heap's internal array, which takes O(n) time. This direct loading process corresponds to randomly placing the elements into the nodes of a complete binary tree, as illustrated in the figure on the right. Note that no sorting is performed at this stage. The elements are simply arranged in the array as they appear. Next, we will rearrange the data elements to restore the heap property using the following rule. Starting from the last non-leaf node, iteratively down-percolate each preceding node in the heap's internal array. In the example shown on the right, nodes D, E, and F are leaf nodes. Therefore, the last non-leaf node is C, which is stored in array index 2. The process begins by down-percolating node C. Next, we down-percolate node B, which is located at the array index preceding node C. Finally, we down-percolate node A, which is stored at the array index preceding node B. To begin, we down-percolate node C by swapping its value with that of its left child, node F. Next, we down-percolate node B to restore the heap property of its subtree. Finally, we down-percolate node A to complete the heap construction process. After completing the series of down-percolations, we obtain the tree shown on the right. You can verify that the heap property has been fully restored in this tree. In summary, the construction operation consists of two main steps. First, load the data elements in a complete binary tree to ensure the structural property of the heap. Second, starting from the last non-leaf node, down-percolate the nodes from right to left and bottom to top. this series of down percolation restores the heap property. Next, we will address two key questions. First, why does the series of down percolation properly restore the heap property? And second, what is the overall time complexity of the heap construction operation? We begin by proving the correctness of the construction operation using method induction. First, we establish the base case. Let the array index of the last non-leaf node be m, and the corresponding node be tm. We claim that for any array index x, such that x is greater than m and less than or equal to n, the subtree rooted at tx is a valid heap. The claim holds because tm is the last non-leaf node. Consequently, if x is greater than m, the node tx must be a leaf node. A subtree rooted at a leaf node contains only the node itself. Since a single node tree satisfies the heap property by definition, the subtree rooted at tx is a valid heap. Next, we make the induction hypothesis. We hypothesize that after k down percolations, any subtree rooted at tx, where x is greater than n minus k and less than or equal to n, will become a valid heap. In other words, we assume that all the blue subtrees shown in the figure on the right are valid heaps after k down percolations. We now need to show that after the k plus 1th down percolation, which will be applied to the node t n minus k, the subtree rooted at t n minus k will also become a valid heap. For the node t n minus k, its two children must have array indexes greater than n minus k. By the induction hypothesis, the subtrees rooted at t n minus k's children are already valid heaps. In this case, the only possible heap property violation within the subtree rooted at t n minus k would occur between the node t n minus k and its two children. This scenario is identical to the decreased key case. As proven in the previous video, downpercolating the root node in such a scenario can restore the heap property for the entire subtree. Therefore, downpercolating Tn minus k will restore the heap property for the entire subtree rooted at Tn minus k, making it a valid heap. In other words, we have proven that after k plus 1 downpercolations, any subtree rooted at tx, where x is greater than n minus k minus 1 and less than or equal to n, will become a valid heap. Hence, after the series of downpercolations, the heap property for the entire subtree will be restored. In conclusion, the construction operation is correct. Next, we will analyze the time complexity of the construction operation. From the previous video, we know that the total number of swaps performed during a single downpercolation is upper bounded by the height of the heap, which is O log n. Therefore, the time complexity of a single downpercolation operation is also O log n. Since there are at most n nodes to downpercolate, the total time complexity of the construction operation seems to add up to O n log n. However, this estimate is overly conservative, which assumes that all nodes are at the maximum height of the tree. In fact, because a heap is a complete binary tree, most nodes are closer to the leaves and require fewer levels to downpercolate. This difference can dramatically reduce the overall time complexity. We will now analyze this in more detail and show that the construction operation actually runs in ON. To do so, know that we can find the upper bound for the number of swaps made in a single construction operation by summing the heights of all nodes in the heap. Denote the height of the heap as h. We claim that the sum of all nodes in the heap is given by 2 to the power of h plus 1 minus 1 minus h plus 1. To prove the claim, know that there is one root node in the heap, and its height is h. There are two nodes in the second layer, and each node has a height of h minus 1. In general, at the ith layer, there are 2 to the power of I nodes. Each node at this layer has a height of h minus I. We can then sum the heights of nodes in all layers as the formula shown in the first line of the slide. Essentially, the total heights of nodes in a layer can be computed as the total number of nodes in that layer multiplied by the height of that layer. As a result, the sum S equals to h plus 2 times h minus 1 plus 4 times h minus 2 all the way through 2 to the power of h minus 1 times 1. The first term of the formula, h, corresponds to the single root node, which has a height of h. The second term of the sum, 2 times h minus 1, accounts for the two nodes at the second level, each with a height of h minus 1. This pattern continues for all levels of the heap. To simplify the sum, we multiply the entire sum by 2, which leads to the equation shown in the second line in the slide. That is, 2s equals 2h plus 4 times h minus 1 plus 8 times h minus 2 all the way through 2 to the power of h times 1. Then, subtract the original sum shown in the first line from this new equation. During this subtraction, many terms can be cancelled out. For example, subtracting the green term in the first sum from that in the second leaves 2, and subtracting the red term in the first sum from that in the second leaves 4. In this case, the remaining terms resulted from the subtraction form a geometric series with a common ratio of 2. Thus, the result of the subtraction simplifies to s equals 2 to the power of h plus 1 minus 1 minus h plus 1. In other words, the sum of the heights of all nodes, as well as the total number of swaps performed in a construction operation, is upper bounded by 2 to the power of h plus 1 minus 1 minus h plus 1. We can further simplify the result by discarding the minor terms and approximate the upper bound for the construction operation as O 2 to the power of h plus 1. Since a heap is a complete binary tree, its height h is in O log n. Substituting h equals O log n into the expression of O 2 to the power of h plus 1, we find that the time complexity for the construction operation is On. The construction function is implemented using a simple for loop. It iteratively downpercolates the nodes in the heap's internal array, working in reverse order from the last non-leaf node to the root. In summary, we have presented the heap construction operation, and prove that it runs in linear time O(n). Thank you for watching, and see you next time.